Hi, so I'm going to talk about electric potential. So first, I set my coordinate system, calling this the x positive direction, the y positive direction here. Put this to the side, and I have a positive charge q here, positive charge. And infinitely far away, I have a little test charge, little q. It is negative infinity, 0 away. And I want to find the work of bringing this charge all the way to, let's say, this point called point P. I want to find out how much force I need to push on this charge to this point called point P. And I could do this by integral. The force between these two charges is given by K Q divided by R squared and times the unit vector. So the integral we have, so the work external equals to the integral from negative infinity to point P, K, Q, little q, R squared dr. And if we solve that integral, we can bring this is a constant up on the numerator, and solve this. This will give us KQQ negative 1 over R evaluated from negative infinity to P, and we get KQQ R. So the work external equals to K big Q times little q divided by R, where R is the distance between this is R. So electric potential, what it is essentially, for example, we know that this charge, this little q, is arbitrary. It's arbitrarily picked as a test charge. We want something more concrete in our space of interest. So it's defined electric potential is defined to be the work external divide by Q. Basically, work external per unit charge. And what does that mean? That means the work I need to do to bring this charge from negative infinity to P per unit charge. Divide by the charge that I'm moving. This may seem a bit abstract. And we want to write electric potential in terms of big Q's electric field. How do we do that? So one of the conditions in the definition is that I'm moving this charge. The charge is being moved at constant velocity to point P. So this charge is moving at constant velocity. For example, when the charge is over here, when little q is over here, it will sustain an electric field force Q QE in the negative direction. But I am pushing this force with positive Q times E. They cancel out. They cancel out. So if I want to define this as, if I want to define electric potential in terms of the electric field that a test charge is sustained in, first, let me back up a little here. This is KQ over R. We divided Q. And the work that I've done, it can also be written, because I'm saying that I'm doing pushing this in the positive direction with magnitude QE. It could also be written as negative infinity to point P. So QE dot dr. Very good. However, the electric field of interest here is in a negative direction. The electric field is pointing in the negative direction. So how do we fix that? Well, since E is pointing in the negative direction, since E is pointing to the negative direction, actually I need to put a negative in front of the integral. So basically what's happening is we initially have negative QE dot dr. However, this is the force, this is the negative force that the electric field is doing on the charge. I need to calculate the work that I've done on the charge. The electric field is providing negative work while the external force is providing positive work. So, however, electric potential is defined to be the work external, not the work by the field. This is really, very, really important. It's the work external, done by external force, not the work done by the field. So I need to add a negative in front of here. So the work done by E is this integral evaluated from negative infinity to P. However, electric potential is defined as the work per unit charge. So V is 1 divided by 1 over Q, the integral of P negative from negative infinity to P, QE dot dr. Thus, V is given by from negative infinity. Sorry, just a negative here. So V is given by the integral from negative infinity to P Q times E dot dr. Sorry, it's just E dot dr. And because it's usually this equation is written in this way. V equals negative B from A to B E dot dr. We're just switching negative infinity to P. Basically, it's P E dot dr, and this is how the equation goes. Sorry, that's a really bad square. So this is the basic definition of electric potential. So now let's talk about conducting shells, because that seems to be like a big topic. And I'm going to evaluate it based on these 4 regions. I call this region 1, region 2, region 3, and region 4. So the first region where R is greater than D. Where R is greater than D, since the net charge of these 2 shells, note that these are 2 conducting shells. There are 2 conducting shells, and this one has thickness, by the way. This one has thickness. Just gonna watch. Has thickness. It's not one-dimensional. So, we can evaluate this by Gauss's law. E dot dA equals the charge enclosed, the net charge enclosed, divided by epsilon naught. And the charge enclosed here is 4q plus negative q divided by epsilon naught, meaning it's 3q divided by epsilon naught. Great. And because this is a sphere and the dot product is always the cosine of the dot product is always going to be 1, so E times 4 pi r squared equals 3q over epsilon naught. Thus, the electric field when r is larger than d, the magnitude of the electric field, equals to 3q 4 pi r squared times epsilon naught. Great. So, what about between B and C? Basically, this region. I said this is a conductor, okay? This is a conductor, and inside a conductor, because of the charge arrangement and everything, the electric field must be 0. So the electric field is 0 at that point. What about between A and B? Between A and B, because, for example, if we draw ourselves a Gaussian right here, a Gaussian surface, it's enclosing 4q. So we could do the same thing we did in region 1. E dot dA equals the net charge enclosed divided by epsilon naught. That means it's 4q epsilon naught, and this will give us E times 4 pi r squared equals to 4q epsilon naught, and thus E equals 4q 4 pi r squared epsilon naught. I'm gonna simplify just for the sake of things. Pi r squared epsilon naught. Okay. And you may wonder why. Okay, so why this is the case? I'll explain it later. I'll explain it later. Give me a moment. So when r is less than a, because this is also a conductor, E equals to 0. E is also equal to 0. So, okay. Things I need to point out here. First, the net charge of this outer shell is negative q, but it doesn't mean that this spot is negative q. What do I mean by that? So, we know that the electric field inside this region that I'm shading in is 0. It equals 0. That's a given. That's a must because the shell is a conductor. This means that the Gaussian, if we draw a Gaussian surface inside the thickness of this sphere, it's the Q enclosed in this Gaussian surface that I drew must be 0. So the Q enclosed must equal 0. However, I'm already enclosing 4Q. So 4Q minus Q inner, basically this spot right here, I'm highlighting right here, this entire circle must equal to 0. So Q inner must equal that's plus. Q inner must be negative 4Q. Means that around the edge of this circle right here, it has negative 4Q, so negative 4Q. And that means the outside, Q outer, and plus Q inner equals to negative Q. That means Q outer equals to negative Q minus Q inner. Q outer must equal to 3Q because negative Q plus that's 4Q. Well, that's negative 4Q. Negative, positive. So that's 3Q positive. So the outside here have 3Q positive. Okay, so let's find the electric potential of everything. I will just move this downwards a bit. So the electric potential, let's start with region 1 and work our way all the way to 4. So let's start with, so it's going to be 4 integrals. It's going to be 4 integrals. And this is how it's going to go. So let's start from region 1. I'll just get this out of the way still. So starting from region 1, V of region 1 equals to the integral from negative infinity to, alright, so we're d squared and d. Let's say region 1, let's say all the way till this. Let's say all the way till this point right here, till point C. C, and that's going to be dr, and that's going to be from negative infinity to C. That's going to be 3Q 4 pi r squared epsilon naught dr. Well, this is a negative sign here. There's negative signs here. And this one is going to be from V2. This is from, let's see what this is. This is from C to B. Notice that our functions must be continuous, so the bounds must also be continuous. Dot dr. And because the potential, this is, okay, this is a concept, okay? So I should not have this interval. So the electric field is 0, yes, but because we have a conducting shell, the inside of the sphere, the inside of a conducting shell has potential equivalent to the outer shell. So what I'm basically saying is that is from C to B. Has a electric potential magnitude of 4 of this r squared epsilon naught dr. And let's move on to V3, which is very similar to region 1. Region 1 is from A to B, and it's from B to A. It's from B to A. And we are given, and the electric field that we calculated right here is Q pi r squared epsilon naught dr. These all have negative signs. Why I keep forgetting my negative signs, I don't know. And V3 is very similar to the logic of 2. It's going to have similar magnitude. So depending on whatever point you want inside, let's just say you want the potential to be, you want to find the potential at this point. Let's call it point X. It's negative infinity from A to X. Sorry. Negative A to X. It's basically A to X. And that's going to be Q for, the force cancel out, and that's going to be pi r squared epsilon naught dot dr. And the net potential for bringing a charge all the way to point X, basically electric potential of bringing a charge from negative infinity to point X equals to V1 plus V2 plus V3 plus V4. There we go. And one more thing I want to talk about, which I actually left it here. It's an insulator. An insulator with a uniform distribution of charge. So it has a charge of Q, and if you want to find the charge at this, like the potential at this point, we have to first find the electric field. So the electric field at this point I'm going to use a new integration variable. I'm going to use dx here, okay, as the integration variable because I use r here. is going to be from when when um, when x equals to r. It's going to be, you can calculate from the Gauss law. Dot dA equals to charge enclosed over epsilon naught. E equals Q 4 pi r squared epsilon naught. And this is, and because at this point we're still enclosing a charge of r, a charge of q, so x equals r has the same electric field. But what about within this point A? Well, it's uniform, so we can find density. So because I'm saying this is of sphere, of not hollow sphere, but solid sphere, rho is defined as Q over V. And V here is given by V equals volume of a sphere, pi r to the third. So rho equals to Q over 4 over 3 pi r cubed. So this ratio must maintain anywhere throughout the sphere. Which means that within at A, it must also maintain the same ratio. So what I mean is that, for example, at A it has a charge of Q1. It must maintain this ratio. That means it's also 4 over 3 pi A cubed. And of course we could eliminate these, eliminate that, and we get rho and that means we get Q1 equals A to the third Q divided by R cubed. This is the charge we have, and we could continue with a Gaussian. We know we just found the amount of charge within this circle. Sorry, the circle could be better, but within this circle, and we could do Gauss law again. So essentially what happens is that E dot dA again, doing a lot, and it's basically Q1 over epsilon naught A to the third Q R cubed divided by epsilon naught. And this will get you, for the flux, A cubed Q divided by epsilon naught times R to the third. And E times 4 pi A squared equals to A cubed Q epsilon naught R cubed, and E equals to AQ 4 pi epsilon naught R cubed. So And we have two electric field equations here. Then we duplicate that. We have two of them here. One is basically from negative infinity to R. And one is from R to A. So we have another integral. There's a series of integral. So let's call this V1 and let's call this V2. So V1 equals to the negative integral E dot dr, and this, we're using dx here, so it's gonna be R, and that's negative infinity, and that's gonna be Q 4 pi x squared epsilon naught dx, and V2 equals to from negative infinity to R. It's gonna be R to A times Q 4 pi epsilon naught R to the third dx, and that's gonna be x squared. Okay, and the potential, trig potential from bringing a charge from negative infinity to A is V1 plus V2. And that will be all. Thank you.